Unit 4, also known as the first half of trigonometric functions, is heavily based around ideas concerning values in radians, types of angle formulas, and proving trigonometric identities. The first major transition occurs through the conversion of degrees to radians. The radian is a unit of measure for an angle. A simple formula allows for conversion of an angle in degrees to radians. This formula is radians equals pi over 180 all multiplied by theta. In Part A of this problem, we are required to convert the four special angles from degrees to radians. This formula can be applied to convert these angles. To demonstrate, let's begin with an angle of 90 degrees. A value of 90 would be plugged into the equation as theta, resulting in the equation reading as radians equals pi over 180 all multiplied by 90. Multiply 90 with the numerator, which is pi. Radians should equal 90 pi over 180. Then, like any other fraction, we would reduce the equation, resulting in radians equals pi over 2. All in all, the conversion should result in an answer of pi over 2 radians. Now, please pause the video and continue to convert the remaining three angles into radians using the same strategy. Your remaining answers should be as follows. 0 degrees equals 0 radians. 360 degrees equals 2 pi radians. 180 degrees equals pi radians. And lastly, 270 degrees equals 3 pi over 2 radians. Please take the time to review and check your answers before we move on to Part B. The second half of the question states that there is an angle of 420 degrees located within a quadrant on a Cartesian plane. We are required to convert this angle to radians, sketch it in its correct quadrant, determine its principal angle, as well as determine the exact trigonometric value for sine. Using the conversion formula, we can convert 420 degrees to radians by first substituting 420 degrees for theta, secondly, multiplying it into the fraction, and lastly, reducing it accordingly. 420 degrees should result in an answer of 7 pi over 3 radians. Now that we have our angle value in radians, we can go ahead to the sketching portion of the question. Knowing that the denominator of the fraction is 3, we must divide the top half and the bottom half of the Cartesian plane into 3 sections each, 3 on the top and 3 on the bottom as follows. In total, there should be 6 lines drawn on the entirety of the Cartesian plane. We must determine which quadrant the numerator of the angle 7 pi lands on. This can be determined by using the 6 lines we marked earlier. Beginning in the first quadrant, in a counterclockwise direction, we can begin drawing the path that it takes to hit the 7th line. We can see that 7 pi lands in the first quadrant of the Cartesian plane. We can go ahead and draw in the angle, labeling it as well. It can be observed that pi over 3 is the principal angle as 7 pi over 3 lands on the first marked line. 7 pi over 3 is essentially equal to pi over 3. Pi over 3 is an angle found in one of the 2 special triangles. Applying the special triangles will determine the exact trigonometric value for sine. As a visual aid, feel free to draw the special triangle. Now, according to SOHCAHTOA, we know that the sine of an angle equals opposite over hypotenuse. If theta is equal to pi over 3, we must determine the opposite and the hypotenuse. The opposite side length from pi over 3 happens to be root 3. The hypotenuse for the triangle is 2. Opposite over hypotenuse equals root 3 over 2. Therefore, the sine of pi over 3, or 7 pi over 3, should be equal to root 3 over 2. Feel free to verify using your calculator. Now we can continue on to compound angle formulas and double angle formulas.
Let's start off by establishing the compound and double angle formulas. Alright, so the first compound angle formula is cos x plus y is equal to cos x times cos y minus sin x times sin y. Next, cos x minus y is equal to cos x times cos y plus sin x times sin y. The next one is sin x plus y is equal to sin x times cos y plus sin y times cos x. Sin x minus y is equal to sin x times cos y minus sin y times cos x. The last two compound angle formulas are tan x plus y is equal to tan x plus tan y all over 1 minus tan x times tan y. And finally, tan x minus y is equal to tan x minus tan y all over 1 plus tan x times tan y. Next, the double angle formulas are cos 2x is equal to cos squared x minus sine squared x, and it is also equal to 1 minus 2 sine squared x. And finally, it is also equal to 2 cos squared x minus 1. The second double angle formula is sine 2x, which is equal to 2 sine x times cos x. And the last formula we are learning today is tan 2x is equal to 2 tan x all over 1 minus tan squared x. Alright everyone, let's get started with this question right here. If angle x is located in quadrant 1 and angle y is located in quadrant 2, such that cos x equals 1 over root 2 and sine y is equal to root 3 over 2. To start, let's draw the axis off to the side here, an angle in the first quadrant and in the second quadrant. We'll label it right here for angle x, along with the square root of 2 being the hypotenuse and 1 being the side adjacent. Moving to angle y in the second quadrant, we'll label it right here for angle y, and we'll also label the hypotenuse as 2 and the opposite side as root 3 while we're at it. Alright, so part A of this question asks us to determine the exact value for cos x minus y. The compound angle formula for cos x minus y is cos x times cos y plus sin x times sin y. Using the diagram and our special angle triangles, we can start subbing in the exact values that correspond with each of the values in the equation. Cos x is equal to 1 over root 2. Cos y is equal to negative 1 over 2 plus sin x is equal to 1 over root 2. And finally, sin y is equal to root 3 over 2. Now that we have the exact values properly in the formula, we can start to simplify. Once we get to this point, we can now rationalize the denominator, and negative root 2 plus root 6 over 4 is our final answer. Moving on to part B, it asks us to clarify whether the double angle formula given 2 tan pi over 6 all over 1 minus tan squared pi over 6 is true for either angle x, angle y, or if it is not true for either. The formula is given is a part of the double angle formulas, which is why we will use it right now. It is also equivalent to tan 2 pi over 6. So we will use that part of the formula, and we can start simplifying with what we know, also while using our special angle triangles. Once simplified, we are left with tan pi over 3, which, while looking at our diagram and our special angle triangles, that equals to root 3. Looking back at our diagrams, neither of the angles that are given to us result in root 3 when we're looking at our primary trig ratios. Tan is equal to opposite over adjacent, which in our diagram would equal negative root 3. Therefore, know the formula 2 tan pi over 6 all over 1 minus tan squared pi over 6 is not true for either angle x or angle y. All right, so there you have it. That is how you are able to use compound and double angle formulas to simplify angles on a plane.
Okay, now that we've discussed how to solve double angle and compound angle formula questions, let's look at how we apply them. In today's question, we will be looking at how to use these formulas when working with angles on a plane, and deciding which formula is most appropriate for the question you're working with. I will bring up the formulas on the side so we have them to refer to throughout this process. So the question reads, if secant theta is equal to negative 5 over 2 and theta is between 0 and 2 pi, find the values of cos 2 theta and sin 2 theta. I like to start off any type of these questions by drawing a diagram, so I can better visualize the plane. We know from the question that secant theta is equal to negative 5 over 2, and we can use our reciprocal formula to know that cos theta is then equal to negative 2 over 5. Let's draw the possible values on the grid, knowing that cos is equal to the x over the radius. Using our cast rule, we know that this value can exist in either the second or third quadrant, as the cos value is negative. We should keep that in mind when deciding how many answers we have. For the purpose of teaching this lesson, let's look at the first part of this question, finding cos 2 theta separate from the other part. When looking at our formula sheet, we can see that there are many different options to choose from when solving for cos 2 theta. But usually there's one formula that will be easier or have less steps involved when finding the answer. Currently, we do not know what sin theta is, though we will have to solve for it in the second part of the question. But let's ignore that for now. So the most appropriate formula to use in this situation is that cos 2 theta is equal to cos squared theta minus sin squared theta. If we were given sin theta and not cos theta, this formula would be more appropriate. Let's get back to answering the question. We can now substitute cos theta into the formula and solve it like we would any other equation. We would follow BEDMAS and square the substitution first, then multiply it by 2, and then subtract the 1. And there we have it. The answer to part A is negative 17 over 25. Now let's move on to the second part of the question, finding sin 2 theta. As we only have one formula for this, we need to first find all the variables in the formula. We already know the value for cos theta. We now need to find the value for sin theta. Sine is equal to the opposite over hypotenuse. and we already know what the hypotenuse is. We just need to find O. We can use the Pythagorean theorem to do this. Let's go ahead and do that. We get plus or minus the square root of 21 as our opposite value. Going back to our grid, we can see that this answer makes sense, as there are two possible answers for what O can be, and there is a positive and negative value for every square root answer. The next step is to go and substitute our values into the formula and solve for our answer. Let's go ahead and do that. We then solve this like we would any other equation by multiplying all these answers out. We can repeat this process for both values of sine theta, but they would just change the sign. So there's a positive and a negative answer. And there you have it. You are now able to solve application questions for double angle formulas on a plane.
Let's take a look at our communication question for this unit. Explain why verifying the two sides of a trig identity for given values is an insufficient method of concluding whether an identity is valid or not. So essentially, the question is asking us to explain why solving identities by subbing in values is an insufficient method of determining whether the identity is valid or not. Remember that an identity must be true for all factors of x in order to be considered valid. Now, verifying by subbing in a value shows that the identity is true for that particular value of the variable. However, it doesn't prove that the identity is valid for all other values of x. For example, let's take a look at the equation tan of x equals sine x over cos x. By subbing in pi for x, we can solve to determine that both sides equal to 0. Therefore, the identity is proved to be true, but only when pi is the value of our variable. We haven't determined if this identity is true for all other values of x. Also, subbing in values isn't a reliable method because our results won't always be accurate. Some values of x can make it seem as if the identity is valid when in truth it isn't. For example, sine of x doesn't equal to cos of x, but when we sub in pi over 4 for x, then the equation equals to one another, giving us the false impression that the identity is valid. Well, how do we know that it's not an identity? If we sub in pi over 6, then the left side doesn't equal to the right side, and in order to be qualified as an identity, all values of x must be true to the equation. Unlike solving an equation where we rearrange to solve for our variable and plug in values for x, with identities we must use logical steps to show that one side of the equation can be transformed into the other side of the equation. For example, tan x plus 1 over tan x equals 1 over sine x cos x. Now, if we manipulate one side of this equation to make it look identical to the other side, we can determine whether it's an identity. If the left side is equal to the right side, then it's an identity. If not, then it's not an identity. Notice how we aren't plugging in values for x. The reason subbing in values is an insufficient tactic to solve identities is because identities have an infinite number of solutions, and so they must be proved by making sure both sides of the equation are identical to one another. By plugging in values for x, we make the situation more complicated and longer. So if we just manipulate one side into looking like the other side, that's more of an effective way to solve an identity.
Now, for our thinking part of our unit, we will be learning how to prove trig identities. Before we prove an identity, let's take a look at some basic known identities. Here we have reciprocal identities. First is cosine x is equal to 1 over sine x. Then we have secant x is equal to 1 over cos x. Lastly, there's cotangent x is equal to 1 over tan x. Our next set of identities are quotient identities. First we have tan x is equal to sine x over cos x. Then there's cotangent x is equal to cos x over sine x. Lastly, we have our Pythagorean identities. First, there is sine squared x plus cosine squared x is equal to 1. This can be arranged so that sine squared x is equal to 1 minus cos squared x, or cos squared x is equal to 1 minus sine squared x. Some other Pythagorean identities are 1 plus tan squared x equals secant squared x, and 1 plus cotangent squared x is equal to cosecant squared x. Knowing these simple identities along with our double and compound angle formulas from our other lesson will help us solve more complicated identities. Just one more thing before we begin. Here are some helpful tips. Number 1, always start out with the more complicated side of an identity. Number 2, use your known identities and compound and double angle formulas to simplify. Number 3, factor if possible. Number 4, if you get stuck, just try again. Alright, it's time to start proving identities. Let's start out with an easy example. Here, our left side is equal to cotangent x plus 1 over cotangent x, and our right side is equal to 1 over sine x cosine x. Let's start by simplifying our left side. We're going to use our quotient identities to simplify cotangent x into cos x over sine x. This gives us cos x over sine x plus 1 over cos x over sine x. We can then simplify 1 over cos x over sine x into sine x over cos x. Now we're going to create a common denominator of sine x times cos x for both fractions and add them together. This leaves us with cos squared x plus sine squared x over sine x times cos x. If we remember our Pythagorean identity, we know that cos squared x plus sine squared x simplifies to 1. And guess what? You're done. The left side now equals the right side. Okay, time for a harder example. On our left side, we have sine 2x over tan 2x. On our right side, we have cos 2x. We're going to start out by simplifying the left side. Do you remember your double angle formulas? Well, it's time to use them. Simplify the given double angles in the numerator and denominator. Sine 2x becomes 2 sine x cos x. And tan 2x becomes 2 tan x over 1 minus tan squared x. Now we're going to simplify our fraction 2 sine x cos x over 2 tan x over 1 minus tan squared x into 2 sine x cos x times 1 minus tan squared x divided by 2 tan x. Now you can cross out the 2's from the numerator of one fraction and the denominator from the other. Next, we will use our quotient identities and turn all the tan x's into sine x over cos x. To simplify the numerator in the second fraction, we will change the 1 into cos squared x over cos squared x. Then we simplify our numerator into cos squared x minus sine squared x over cos squared x. We will now simplify this fraction further so that we can cross out the cos x. This leaves us with sine x cos x multiplied by cos squared x minus sine squared x over cos x sine x. As you can see, sine x cos x and cos x sine x are the same, so we can cross them out to simplify. This leaves us with cos squared x minus sine squared x. If we remember our double angle formulas, cos squared x minus sine squared x is equivalent to cos 2x. which is the same as our right side. Well, that's it, and I hope this lesson helped you understand how to prove a trig identity. See you next time!